All right, I hope everybody isn't getting too frustrated. Welcome back, by the way. Really, the best way to get good at these types of things is to just work a lot of problems. Your brains will wrap. It's real tricky right now. I know it's pretty abstract right now, but we're going to work some problems. We're going to do a ton of problems in class, and by the time we're done, I guarantee you're going to get it. All right, so here we go. Polygraph tests are accurate more than 80% of the time. So the first thing we always do is we write our null hypothesis and we write our alternative hypothesis. Well, again, we're testing a claim around proportion. And this says more than, which implies my alternative hypothesis is going to be P is greater than 0.8. My null hypothesis, I could write it as less than or equal to, or I can simplify the process and say that it's equal to. To be honest with you, when I first started learning, I kind of parenthetically thought about this like that. Okay, you know, it's like less than or equal to. I wanted that thing to be perfectly binary. All right. Now let's make up some data. Let's say that they gave 98 lie detector tests. Okay, and you know, they're not for real lie detector tests. You know, it's not like they tested prisoners because they wouldn't really know if they were lying or if they weren't. And let's say that out of the 98, 80 were accurate, and what do we got? 18 not accurate. All right? So first thing we better check is NP and NQ greater than or equal to 5. Remember that? Because it's kind of like a binomial deal. Should be relatively easy to see that. 0.2 times 9.8 is going to be close to 20. 0.8 times 9.8 is going to be pretty close to 80. So I think we're in good shape. So check. All right. Now we're in business. Now here's a problem. Because of this alternative hypothesis, instead of being two-tailed, this is called a one-tailed. And any time that you have a one-tailed, we can't use, this implies no confidence intervals. You can only use confidence intervals on two tails. Hopefully you can figure out why that is. Maybe not. All right, but that's okay. You'll figure it out down the road. Now the other thing that we're going to need to pick out is we're going to have to pick out an alpha level. All right, we're going to figure out what is an acceptable level of variation. In other words, how much probability that we're going to be dead wrong, that we're going to assume the exact wrong thing are we going to allow. Again, the union standard is about 0.05, is at 0.05. So alpha equals 0.05. At this point, we are committed. Now, if we wanted to, we could go 0.01. We could go 0.1. But 0.05 is going to be recognizable by a lot of people, and they're going to be like, okay, this guy or gal knows what they're doing. Now, again, we can't do confidence intervals, so let's go with, we're going to do critical. Let's do critical value first. Down the road, I'll switch these around, and we'll do p-values first. All right, remember, sample proportions distribute themselves normally. They're an unbiased estimator. All right? So, notice that this is a one-tailed. Now the question is where does the tail lie? In other words, where is this critical region going to lie? All right? If my claim is that they're more than 0.8, then what I have to do is I have to prove beyond a shadow of a doubt that my value is going to be way or enough above 80% to be able to throw out the null hypothesis. The null hypothesis always contains the equality. So what that says is I want the value for 0.05 right there. That's what alpha is. If alpha is 0.05, then I now want the critical value that cuts this off. Because if I end up with a critical value inside of this region, then that is far enough away from my mean or my assumed population proportion of 0.8 to say, hey, something's fishy. Now, I'm going to show you how to find this. So, you ready? Well, I'll stumble up here. Let's go critical value, and it's going to equal. Now, remember, it's on the normal curve. So that's nice. That's a good piece of information. I'm going to escape out of here, get rid of this. I'm going to head over this way. All right? Now, there's lots of ways to do this. Remember, it's a one-tailed distribution. So what I'm looking for is I'm looking for one of two things. Let's real quickly. Let me bring that back up. A lot of times students will say, well, Ripley, how do I know which side the tail is on? Well, notice this guy right here always points in the direction of the tail. It's a greater than, or excuse me, it's a greater than 0.8, but the inequality points in the direction of the tail. So if it were a less than, the tail would be on the left. All right? So there's lots of ways to do this. If I want to get fancy, I can think of this as being, there's 0.95 to the left of whatever this critical value is. All right? So I'm going to head over here because my chart only gives me values to the left, and I'm going to look for 0.95. So check it out. Let me see if I can get the top here so we can see it. 0.95, let's see, 0.945, 0.9505, and I am between 1.64 and 1.65. So what I do is I split the difference and say that the critical region for that happens at right here. This is my critical value, and it's going to be 1.645. Now, in summary, that is the line of demarcation. If my z statistic, if my test statistic gets into this area right here, remember we called this the critical region, or CR, then I am too far away from 0.8, and I can reject the null hypothesis and accept my claim. I reject the null. There's evidence that the null is wrong. If I end up in here. If I don't, there's not enough evidence. I can't do anything. Okay? So let's kick back over into this mode, and let's remember our formula. My critical value is at 1.645. Now, let's test it. Well, the first thing I need to remember, z is equal to p hat minus p over the square root of pq over n. So let's see, I need p hat, don't I? I know what p is. Let's write everything up. Keep it simple. P is 0.8. That's in the null. Q is 0.2. N is 98. And p hat is going to be what? Well, it said that 80 out of the 98 were accurate. I know that's a little bit confusing because of this 0.8 and this, but we're not afraid, right? 80 out of 98, which is equal to 80 out of 98, and that's equal to 0.816. Now, 0.816 is bigger than 0.8, but I hope you're starting to get the idea here. Is it big enough? Okay, well, let's figure it out. 0.816 minus 0.8 divided by the square root of 0.8 times 0.2 divided by 98. All right? So 0.816 minus, what do we got? We got 0.016. Let me throw it in my calculator. 0.016 divided by second square root of 0.8 times 0.2 divided by 98 in paren, and I end up with 0.396. Whoa, how anticlimactic. Look at that. 0.396. That's the z value, which gets me right here. I mean, think about it. On the standard normal curve, this 0.8 turns into a 0. So 0.396 is like right here. That is not acceptable, right? It's not enough evidence to reject the null, which implies, think about that, which implies that the claim itself is wrong. So because, now we're going to write this up nice and clean and nice and pretty, since 0.396 is less than 1.645, there is not enough, we're going to keep it simple, not enough evidence to reject the null hypothesis. It appears the claim is wrong. Is dead wrong. All right, the evidence says it's wrong. Okay, now let's prove it with p-values. So this was the critical value one, right? Now we're going to prove it with p-values. So the cool thing is, again, with the critical values, I've already done the heavy lifting. So now let's do it with p-values. What was my test statistic? What the heck was my test statistic? I know that z equaled what was it, 0.318? 0.3, no, 0.396. Let's go back. So my my charts aren't going to give me that. So really, my z is equal to well, let's go 0.40, because I have to round, because that's how my chart works. I stumble back to my chart. All right, I got a z value of 0.4. You know what? Before I do that, let's see. Think about what's going on. Let's draw our curve here. My critical value, well, I'm not even going to put the critical value. All right, when we go to the standard normal, I get 0. I'm going to get a z equals 0.4, and now what I'm looking for is the probability of getting values at least as extreme. So I go back to my chart, and I'm looking for, the problem is, what are we going to do? Let's look at it. I need to get out of my own way with this here for a second, don't I? Go to z equals 0.40, right? Wasn't that it? Well, z equals 0.40 gives me a probability of 0.6554. All right, let me get my paper back up. So 0.6554. So that tells me that everything to the left over here is 0.6554. If this is 0.6554, then isn't this guy right here, which is the probability of getting values at least as extreme of, what is that, 0.3446, 0.3446. So my p-value equals 0.3446. Now I want you to notice something here. Remember when we had the two-tailed thing, I actually had to take alpha and divide it in half. I had to cut it in half. But because we've got a one-tailed situation going on here, I don't have to cut it in half because I can't miss on both sides. I'm only worried about missing on the high side. So here's my p-value, 0.3446, since 0.3446, which is the probability of getting values at least as extreme as I got. The probability of getting that 0.81, which was our test, which was our sample proportion, well, that's 1 in 3 times. That's to be expected. Since this is greater than alpha, remember, if it was less than alpha, we reject, but since it's greater than alpha, we do not reject. And that's it. That's all there is to it. Okay. Walk it off. When we come back, we'll do some hypothesis testing around means rather than around proportions. All right, I'll give you test statistics and all that good stuff. So